Hi ladies, so we're going to take a look at hybrid orbitals and kind of see why and how the Vesper theory is allowed by the use of these hybrids. So let's just take a look at the word hybrid. Right? So if you take a look at hybrids, you've seen some of them in biology, but let's just take a real world example and take a look at not electric cars, but hybrid cars. What is a hybrid car? Okay, so go ahead and think about that for a little bit. We know that they're gas efficient and that you don't have to use as much gas to go a further distance. But why is that? Right, so if you take a look at a hybrid car, it's a mix between an electric car and a regular car that uses gas. So what they decided to do was, let's merge these two ideas and make a car that can do both, run on regular gas, but still be energy efficient. And that's kind of this idea of hybrids. Hybrids is always a mix of different things. So in chemistry, we have these hybrid orbitals. That's the same concept as a hybrid car. I'm going to take two orbitals, mix them together, and this then allows for this molecular bonding that we see, and which then creates these molecular shapes. So by definition, hybrid orbitals are orbital hybridization, which gives us information about how molecules bond and what the shape is going to look like. The term hybridization itself is when the atomic orbitals that we have used in the past. So this is the use of the atomic orbitals, our sp and d orbitals that we've used in the past. These become mixtures that create different hybrid orbitals. So let's take a look at how this happens with a single bond. So if you take a look, these single bonds, they have hybrids that are called sp3 hybrids. Okay? And we're going to do this example with CH4. Since we've done the 3D structure for this, we're going to find out why is this a tetrahedral shape. So just to recall, when I have an s orbital is the shape of a sphere, right? And let's use our px orbital, our first orbital. We know that our px orbital has the shape of an infinity sign that's on its side, right? Well, if you're to imagine that I have electrons in an s orbital wanting to bond with electrons in the p orbital, what you'll notice is this p orbital is going to get really close to this s. And just like our previous example from last class, we took the idea of two water drops. If these two water drops get too close together, what do they then become? Correct, they become one large water drop. So what we see happening is when this s orbital and this p orbital combine right here, we're going to see that what it's going to create is an sp orbital. So what you are going to see is that we are going to create an orbital that looks like a p orbital, except the difference is the one that connected to the s is really large, and then you have a regular size orbital for the right hand side. So let's actually do this with CH4 and see what the electrons are doing. Okay. So what I'm going to do is we are going to do our electron configuration drawings just like we used to with our arrows and see what's happening to these different arrows. So if I take a look at our central atom, which is carbon, I'm going to draw the different electron configuration that we receive. And so if I take a look, I will always have the first up arrow, and then what we'll see is we'll have that down arrow, right? Carbon has a total of 6, so the next one is going to go up and then down. And then the last two need to be parallel, so it's going to go up and up, right? So for carbon, this is our first step, is draw the electron configuration here. The next thing is I need to do my hydrogens, and so if you take a look at CH4, I need to have 4 hydrogens. So there's 1 hydrogen, 2 hydrogen, 3 hydrogen, and 4 hydrogen. And just to label these, just recall this is our carbon and these are our H's. I have 1 H there, 1 H here, 1 H here, and 1 H here. So once again, these are our 4 H's. And each H has 1 electron. So what I'm going to do is I'm going to put one of these electrons in each one. So here's an up, here's an up, here's another up, and the final up right here. So just watch and see what happens as of right now. What we notice is the first thing that can happen is this electron right here could share with this one right here. Right? And this electron right here can share with this electron right here. But then you notice I still have these 2 other electrons that need to share with someone. And just like we did last time, I can't do that here because this box is empty. And I can't just stick these 2 electrons in here, because if I did that, then they would be bonding with each other instead of bonding with the carbon. We need them to bond with the carbon. So what we're going to do is let's undo all of this. And let's take a look how we can create a hybrid. So once again, by definition, what's a hybrid? Good. And a hybrid model is when I can mix different orbitals. So what happens is this p orbital right here, there's an x and a y that's filled, but this z section is still empty. So what the orbitals do is they say, okay, well, I'd like to fill this, but the only place to get that is if I go down to this s orbital. So these p orbitals communicate with this s orbital and say, hey, why don't you come up here and share your electron with us? And so when this s orbital decides to join and mix with these p orbitals, it then allows this last electron that was here, to move over to this side. So let me move this one over to here to allow for this to start mixing. So just because it's supposed to be, our first arrow should always be up. And so now what we see is that we have created an sp orbital. So the s came from here and the p comes from here. Right? And so now this gives us an opportunity to let these electrons share. So just so I get rid of these, what's going to happen is this electron is going to share with this orbital. This electron right here is going to share with this orbital. And this electron right here is going to share with this orbital. And finally, this electron right here is going to share with this orbital. So now every single H atom is now connected to the central C atom. And so what happens is this electron, and remember we're going to flip these since they are jumping into the second area, but this electron is going to jump and share into here sometimes, other times it's going to be here. Creates this bond of being able to link, right? Same thing with this electron. This electron is going to be able to share into this orbital or share into here, and so forth. So what we end up getting is 4 different single bonds that create this sp3 hybrid orbital. Now let's take a look at VSEPR and how this occurs. So if we take a look at our VSEPR drawing, we know that we're going to have a carbon in the middle, right? And now I've created these hybrid orbitals. And so what you end up getting is this tetrahedral shape of these orbitals that were created. So I'm going to have 4 of these, created 4 of these, and then each one I'm adding on that S-shaped sphere. So please excuse my drawings, but this is what's happening. And what we see is there's an H over here, an H over here, an H over here, and an H over here. And if we take a look at these, we need to figure out, are these sigma or pi bonds? And just as a refresher, don't forget this symbol right here is our sigma. So this is sigma, S-I-G-M-A. And you also know we have our pi orbitals, our pi bonds. So let's take a look and see what kind of bonds these are. So I'm going to start with this one right here. If I draw a line, you notice these bonds are in the same axes, right? And if they're the same axis, are they sigma bonds or pi bonds? Good, they are actually sigma bonds. So what we're going to do is we are going to label this as a sigma bond. Okay. I take a look at the next one and I notice that this is also on the same axes, which means it is another sigma bond. On here, this bond is also on the same axes, right? And that means this one is also a sigma bond. And finally, on this last one, these ones are on the same axes, which gives us the fourth sigma bond, or single bond. And just to recall, these hybrids are called sp3 hybrids. Good. So now we can do this with our single bond electrons. Our single bonds. Perfect. In the next video, you'll see how we do these with our double bonds. So go ahead and take a look at this and make sure you know how to create these sp3 orbitals.